Thank you very much. Thank you all for coming this evening. So if the introduction had been longer, Lars would have said something about the fact that I'm working on hearing. And I want to begin by motivating our studies and those of others in our field. And I would say there are two broad motives that keep us busy in this area. The first one is a purely scientific set of motives. The ear and our hearing process are really remarkable in their technical capabilities. So as most of you know, we can hear sounds at frequencies up to 20 kilohertz. That's 20,000 vibrations per second. And that's an extraordinarily high number when you contrast it, for example, with vision. You know in vision, if you see a series of images 20 times a second or 30 times a second, you see that as a continuum. That's the basis of television, the basis of motion pictures. But in the case of hearing, stimuli that are 1,000 times faster somehow can be resolved. So this is by far the fastest of our senses in that particular way. A second characteristic that's extraordinary is just how sensitive our ear is. At our acoustic threshold, which corresponds to about 0 decibels, more or less by definition, the eardrum vibrates by a few picometers. That's trillionths of a meter. It's smaller than most atoms. So one wonders how, just a membrane vibrating this ridiculously small amount can send reliable signals into the ear. And the internal workings of the ear that I'll describe in more detail, they vibrate by a few tenths of 1 nanometer. So this is about the size of a typical atom. So once again, how does something made out of proteins and lipids and whatnot reliably respond to such incredibly small stimuli? The third characteristic that's amazing is what's called the dynamic range of hearing, the breadth of stimuli that we can accommodate. So from 0 decibels, the threshold, to 120 decibels, which is about the loudest sound we can tolerate without any damage. That represents 6 orders of magnitude. In other words, a million-fold range in the amplitude of the sound, or a trillion-fold range in the power of the sound. And I don't know of any other kind of detector that can seamlessly accommodate a trillion-fold range of its inputs, but our ear can do that. So that's half the motivation. The other half of the motivation is pretty obvious. It's the clinical motivation. In our society, in this country, about 10% of the population have functionally significant hearing problems. And by that, I mean problems with hearing that affect daily life. For example, interference with the capacity to talk on the telephone or to understand speech in a crowded environment, and so on. That's 30 million people in this country. It's 350-odd million people worldwide with such difficulties. There are problems from a number of sources. There are more than 200 genetic conditions that cause hearing loss, either at birth or at other times during life. There are various drugs, legitimate drugs, such as those for endocarditis, the aminoglycosides, or those for testicular or ovarian cancer, such as cisplatin. Those drugs happen to devastate the cells of the internal ear. So sometimes it's a life or death decision to use those drugs, but as a consequence, a patient may lose some or all of his or her hearing. There is damage to the ear from simply exposure to loud sounds, so-called acoustic trauma. And this can occur in an industrial setting. It used to occur a lot at airports before OSHA got there and put earmuffs on people. It occurs in a military setting. And most damaging of all is what's called presbyacusis, literally the hearing of old men, which is the gradual deterioration in our hearing faculty as we age. By age 65, about a quarter of us have some significant degree of hearing loss. By age 80, it's half. And this problem probably is a compound of daily damage from sounds in the environment. It's less obvious in Santa Barbara than it is in New York, but believe me, there's a lot of noise out there. And also deterioration of the small blood vessels in the internal ear. Just as we have problems with our heart, our toes, and what have you, from deterioration of blood vessels, so the ear gradually declines. Now, the impact of all this hearing loss is appreciable at all ages. As you can imagine, young children who are born deaf or become deaf at an early age are deprived of the ordinary mechanism of acquiring speech and other forms of symbolic communication. And it used to be a problem that some kids were not noticed to be impaired for several years, particularly the first child of a family that didn't have a sense of when speech should normally develop. And fortunately, new tests have been devised that make it much easier to detect abnormalities of speech at an early age, and I'll describe such a test later on in this talk. For the elderly in our population, gradual hearing loss deprives people of contact with their friends, with their neighbors, those in the workplace, throughout their lives. And this can lead to a sense of isolation that is really very depressing to people. Gradually, we've accommodated ways of dealing with that. Hearing aids have gotten better, and they're less stigmatized. It used to be, just a generation or so ago, rather unusual for people to wear hearing aids in public because they were big and bulky and stigmatized people as getting on in years. Ronald Reagan, who to my mind did little else right, was the first public figure to wear hearing aids, and it was in the paper. It was a big deal at the time, but it helped to destigmatize them. And in the next administration, Bill Clinton wore and wears 2 hearing aids, but nobody pays any attention to it. I mean, it's now the norm, no big deal. And finally, for people of the middle years of life, abrupt and unexpected hearing loss, which can happen to any of us tomorrow from viral infections, can really be devastating. Helen Keller, who was of course both blind and deaf, said that blindness deprives us of our contact with things, but deafness deprives us of our contact with people. And we are such social animals that the daily what seem like minor interactions, your conversations as you came in the door, chatting with people you drove here with and so on, those things are really important in setting all of us in our sort of social milieu. And if one is deprived of those inputs, one feels a strong sense of isolation that hearing people just cannot really appreciate. The other thing we lose with deafness is a distant early warning system. You know that if there is a tsunami alert, if there is a fire or something else, or even a car just screeching down the road, you're warned of it some time before the problem gets there. And again, a person who doesn't have the hearing capacity feels a vulnerability that the hearing don't actually appreciate. So in this talk, I'm going to briefly tell you what our ears are doing right now, how hearing ordinarily operates. Then I'll introduce you to the cells that do the work, explain something about their remarkable qualities, and I'll spend the bulk of the lecture talking about what lies in the future, what's being done now at the program in which I'm participating, and what we anticipate in future years, particularly on the clinical side, with dealing with these problems. So let me begin by telling you something about what your ears are doing right now. So this is a segment of human speech. It's 2.5 seconds long. If you recorded what's coming out of my microphone, you would get these pulses representing the different syllables that I'm speaking. This is my own voice, and it's represented below in a so-called sonogram. This is the same information, but now it's broken down in terms of frequency or tone. So the low frequencies are down here, higher frequencies are up here. And you can see there are characteristics such as these stacks of prominent low frequencies or these wispier high frequency notes. And this particular bit is my voice. It's the last line of the Dylan Thomas poem, Fern Hill. As I was young and easy in the mercy of his means, time held me green and dying, though I sang in my chains like the sea. So this is though I sang in my chains like the sea. And you can see these low frequency stacks or vowels. So ang, what is this? My, I'm a Texan. This is my, chains, and so on. And the high frequencies are the consonants. Sang, chains, see, and what have you. And I show you this to remind you of the fact that you have to do this thousands of times a day. I'll use 53,000 phonemes or speech sounds in this particular lecture, and you'll get most of them right. And it's routine. You never think about the fact that during a given day, you'll do 500,000 of these speech sounds, and very few of them will be misunderstood. So it's remarkable. The ear has to, on the fly, break down this complex stuff and decide what is the difference between the sound ah and the sound ah and other sounds based just on the particular stack of different frequencies that happen to be present. In a word, we're very sensitive to frequencies, and I'll give you a short demonstration of that. These will be frequencies that are played and abruptly change. In other words, I'll start out with a particular tone and then vary it by some amount, and you can listen to see the difference. So it starts out very easy. A 2% change in frequency is really obvious. 1% is very obvious. 0.5%. So most people can hear that. 0.2%, 1/5% gets to be hard. And finally, 0.1%, 1/10%, is tough. So trained string players, musicians can detect the last one. The boundary for most people lies somewhere between these two. So the point here is this is a very small fraction. This means if you listen to something that is 2,000 hertz or something like that, you can hear a difference of 4 cycles or the like. And this is to be contrasted with a single semitone on a piano. It's a change of 6%, so 3 times that much. So we can detect something on the order of 1/30th of the difference between 2 tones on a piano. And this very exquisite frequency sensitivity is what allows us to break down complex sounds, to distinguish one voice from another, and to distinguish other sounds in our environment. The apparatus that does that is the cochlea. The name cochlos is the Greek for snail, for obvious reasons. This is a coil structure with about 3 coils. It's about 8 millimeters in diameter, so it's the size of a chickpea or garbanzo bean. It's part of the labyrinth, and the rest of the labyrinth is involved in the apperception of accelerations. So there are 3 semicircular canals, here, here, and here. These are what give us our sensitivity to angular acceleration, so rotations of the head or rotations of the body. And there's also something called the utricle, which is here, and the sacculus here, which are sensitive to linear accelerations, including the acceleration owing to gravity. So I can tell which way is down because this organ is constantly active. And if I move side to side like that, this other organ, the utricle, detects that and allows me to keep upright and know where I am in space. All of these organs have a common embryological origin, and they all use the same type of receptive cell that I'll introduce in just a moment. Now, to give you some idea of how this cochlea works, I want you to imagine unrolling this 8 millimeter spiral into a straight tube. It would be about 30 millimeters long. That's 1.5 inches. It has bone around its outside. Inside, it's filled with liquid. And there's an elastic partition called the basilar membrane running down its length. This is attached to the external and the middle ear. So here's the eardrum, which vibrates in response to sound. And then there are the 3 smallest bones in the body, the hammer, anvil, and stirrup, or malleus, incus, and stapes, that communicate this vibration to the ear. And the last of these, the stapes, has a piston-like quality, so it can compress or rarefy, pull out on the liquid in the upper compartment. So let's imagine that there's an increase in sound pressure, which is the compressive phase of a sound wave. This would push the eardrum in, move the 3 bones to the right, and the last of them, the stapes, would push on this fluid and compress it, forcing this basilar membrane downward. I should say that the fluid in the lower compartment causes this other extensible membrane, the round window, to bulge outward. During a rarefaction, the other half of the sound wave, exactly the opposite happens. Everything moves to the left, the membrane is pulled up. So if this membrane were simple and homogeneous, you would expect it to oscillate like a violin string, the whole thing bouncing as one. And one can detect what actually happens by a rather sensitive technique, making a very tiny hole in the wall of this and using interferometry, shooting a laser beam in, bouncing it off this basilar membrane, and then measuring the reflected light to measure how the oscillation looks. And when you do that, one finds that this is not a simple string. It's sort of a magical string instead. It's a string that's broad and floppy at its top, that is at the apex of the cochlea, so that low frequencies cause vibrations there. It's taut and narrow at the base. So the highest frequencies, 10 kilohertz, cause a vibration there. And the other frequencies are represented in between in a logarithmic progression. So the real secret of this device is what's shown at the bottom. If you listen to a complex device like my voice, or like the piano or any other instrument, this system breaks down the various sounds into their component parts. In other words, the high frequencies will be represented here at the base, the middle frequencies here in the middle, and not lowest frequencies at the top. Helmholtz first realized that this device undoes the work of a piano. Right? A piano has a series of independent strings, each producing a particular note, and what comes out is an admixture of those, a nice melodious sound. The ear undoes that work. It breaks down the sound that it hears and then represents each of the notes at a different position along the length. Here's a dramatization of this. So here you see the ear canal, where you're not supposed to put a Q-tip. If you read the box, the eardrum, this is the ganglion that carries nerve fibers into the brain, and here's the unrolled basilar membrane. What I like about that is that's what's going on in your ears when you hear this. Both ears are rattling away in a similar pattern at a higher frequency, obviously, but this really replicates basically what's happening. So this vibration then needs to be somehow tapped off and a signal sent to the brain. And that's the job of the sensory receptor cells. I'll show you these in a moment, but they're called hair cells, and they're represented here in yellow along the basilar membrane. Each of these is tuned to a particular frequency. So a vibration, say at middle C, will occur right here. Those yellow cells will be excited, and the coterie of nerve fibers attached to them will then carry information into the brain. There are about 20,000 of these nerve fibers shown in blue, and obviously enough, those at the basal end are sensitive to the highest frequencies, those at the apical end to the low frequencies, and others are set in between. So if you listen to a particular speech sound, let's say this word chains, it begins with a ch, which is a relatively high frequency complex with two particular notes. Those will be represented by hair cells in this region and the associated nerve fibers at those two spots. The ains sound has two striking components which are at a lower frequency, and the final s is weaker, so there'll be a weaker vibration here and weaker excitation of the nerve fibers. So all that the brain knows about what's being heard is this series of messages, one after another. So these are coming down what are called label lines, individual nerve fibers, each tuned to a specific frequency, and it's up to the brain to then decide what those mean in terms of what frequencies are present, be they high or be they low, and just how strong each of them is. This is a strong response, that is a weaker one. The cells that do the detection are called hair cells, and this name is sort of unfortunate. It has little or nothing to do with the kind of hair that I'm losing. This is a much smaller scale device, and you'll see in just a second why they're called hair cells. Each of them is a cylindrical cell, and in the mammalian cochlea, each of them is tuned to a different frequency. So there's some 16,000 of these lined up, of which we see here only 100 or so. And so this will go around and around through 3 spirals, with each of them representing a slightly different frequency along the length. Individual hair cells, such as this one here, have this elaborate structure called the hair bundle sticking out of its top. And this is the mechanical antenna that actually responds to the sound vibration. Now, you can see this somewhat better in the experimental cells that we use. These are actually from the ear of a frog because these cells are hardy and relatively easy to study. The cell, like other cells, has a membrane around it. It's about 25 micrometers in its height. It has a nucleus, it has mitochondria and other organelles. It isn't a nerve cell, so it doesn't have axons and dendrites as nerve cells do, but it does make synapses at its base, that is, contact with these nerve fibers that are excited and carry information into the brain. And the key part of the cell is the hair bundle, this little cluster of processes sticking up out of the top of the cell. And that's seen to best advantage by looking down on it in the scanning electron microscope. So this shows this beautiful organ pipe sort of structure with two key characteristics. One is that there's always a short side to the hair bundle, and then the processes get longer and longer and longer as you go across. So it always has this neatly combed look, and it looks like a bevel on, say, a hypodermic needle. The other point is that these little hairs, the processes, don't stand bolt erect. They always tilt over towards each other, forming this sort of conical or TP shape. And that, as you'll see in a second, is important because it means they can interact with each other at their distal ends, at their top edge. These little processes come in two flavors. There is one eccentrically located at the tall edge of the hair bundle, in this case with a 1 micrometer ball on the top. This one is called a kinocilium, and kino is meant to suggest kinetic, the idea that this is a cilium that can actually move actively. This is like the cilia on sperm tails and bronchial epithelia. It has what's called an axoneme with microtubules and a type of motor called dynein. But the ones that do the work, or all the rest, they're called stereocilia. They're anywhere from 20 to 300, in this instance about 60. The name stereocilia means a stiff or rigid hair, which indeed these are, as you'll see in a moment. So each of these has at its core a lot of the protein called actin, which also is a component of muscle. And this core of actin then has membrane folded over the same way that the fingers of a glove fit over your individual digits. This demonstrates the behavior of a hair cell or hair bundle when it's confronted with a mechanical stimulus. So here's a hair bundle of a living cell. I'm touching it with this glass rod, and when I do so, there are two noteworthy things that happen. First, the hair bundle moves and moves as a unit, so it doesn't fly apart. And as you'll see, that's because there are various types of connections between the stereocilia. And secondly, the individual stereocilia don't bow along their length. Rather, they remain straight and pivot at their base. So if you look at this longest stereocilium here, it's quite straight at rest, and it's equally straight after a stimulus is applied. So if each of these remains straight, but they pivot at their base, it follows that there must be a shearing motion between them. In other words, two adjacent stereocilia in contact like this are going to slide or shear at their tips with respect to each other. And that's key because it turns out that that's where the action is. Various experiments showed that the transduction or conversion of this mechanical input, such as a sound input, occurs not at the bottom where these stereocilia bend, but at the top where they slide. The way this occurs is that there's an apparatus there called the tip link. So the tip link is a fine filament. It's made of molecules called cadherins. It extends from the top of each shorter stereocilium to the side of the next longer stereocilium in front. So there'll be a total of something like 40 of these in the hair bundles that I'm showing you now. The way in which these transduce the input is very simple. Each of these has at its base one or more likely two channels. These are mechanically sensitive ion channels. And as many of you know, a channel is a protein that sits in the membrane and it has a hole in it so that ions, such as sodium and potassium ions, can go through it and carry charge into or out of the cell. And that's the way that nerve cells conduct electrical signals. So at rest, these tip links are attached to channels, but the channels are closed. They have a tiny little gate that's shown here in red. If one applies a mechanical force to the system, pushing it in the positive direction, that is towards the tall edge, there will be a shearing or sliding between the adjacent stereocilia, as I just showed you. And as a consequence of that, there'll be increased tension in each of these tip links. That pulls the channels open. So this is a really simple Mickey Mouse sort of transduction apparatus, but it has two really neat features to it. First, it's blindingly fast. You don't see any chemical reactions in this picture. Photoreceptors of our eye, by contrast, have dozens of very complicated chemical reactions that make them exquisitely sensitive, but make them much, much slower, hundreds and hundreds of times slower. And secondly, there's no intrinsic threshold, by which I mean an arbitrarily small stimulus will cause some increase in tension, some increase in the probability the channel is opening, some increase in the current flowing into the cell, and therefore some increase in the excitation of the system. So the great sensitivity of the system down to the nanometer level stems from the fact that any tiny stimulus can engender a response if the cell simply takes time enough to determine that it's really hearing something and is not being influenced by mechanical noise. Now, there's a striking consequence of this that I'll give you a brief demonstration of. Maybe, where's some light? Can you see me over here? This represents an ion channel. Okay, you can see there are no tricks. It's got a gate, it's got a pore, and it has a tip link. So imagine that this is one stereocilium and this is the next stereocilium with the tip link bridging them. What I've been telling you is that as you listen, as you make a sound, this apparatus moves back and forth, and every time it slides back and forth, the channel opens, and every time the channel opens, some ions run in, and produce an electrical response in the cell. Now the prediction is the following. Let's suppose you came up and pushed on my arms, pushing in the positive direction to your right. As you push, you'll do some work expanding the rubber band, and it'll be the same amount if the channel is closed or if the channel is open. But the interesting thing happens if, as you push, you start with the channel closed, but as you push, the channel opens. Then the rubber band goes slack, and then it tightens up again. So the prediction is there should be a narrow regime, a narrow position in which the hair bundle becomes softer because this elastic band has gone slack and there's less tension in the system. And so we can actually plumb that by doing experiments in which we apply mechanical forces to the hair bundle. Now, I've brought a hair bundle with me tonight, thanks to the local police who didn't catch me, and if they did, I would have told them that you did it, that you required it. But the idea is we have a flexible rod, and this rod in reality is 100 micrometers long. The hair bundle is, in fact, in this case, 100,000 times smaller than what I show you here. So the experiments are somewhat less casual than what follows. But the idea is that you walk up to the hair bundle with this rod and you push its tip varying amounts. And if you look, you'll see that this fiber that I'm pushing with is flexing a certain amount. So if I know how stiff it is and how much it flexes, I can say how much force I'm applying to the hair bundle or how much force the hair bundle is conversely applying to me. So we can therefore characterize the mechanical properties of this device by this simple mechanism. So the way we actually do the experiment, thank you, Craig, is shown here. We stick the fine glass rod to the top edge of the hair bundle. We cast a shadow of that onto a photodiode, magnifying it about 1,000 times. And then we can measure this motion with a precision of better than a nanometer and a frequency resolution of better than 1 kilohertz. When we move the base of the fiber, it pulls the hair bundle in the same direction, but because the fiber is flexible, it bends back to your left. And by measuring how much it bends and knowing how stiff the fiber is, we can determine what force is being produced. And I should say there's a neat trick also for calibrating the fiber. If you look at the fiber, you'll see that it has fine vibrations in it, its tip, even when it's not attached to anything. Now, when I give a lecture, that's because I'm afraid. But in fact, when you do this experiment, it's because of Brownian motion. It's because it's being bombarded by water molecules. And there are theorems that tell you how much vibration ensues as a result of water molecules at a particular temperature and relate that to the stiffness. So we can calibrate these fibers very accurately. When we do the experiment, we see what I mentioned. These devices are not linear. That is to say, the relationship between how much we displace them and how much force we apply does not follow a straight line. That's called Hooke's law. The force is proportional to the displacement. But instead, there's sort of a segue between this straight segment and this straight segment. This represents the situation with all the channels closed, then the channels open, and this represents the segment with all the channels in the open state. Now first, this is a nice demonstration that the theory that I presented to you is probably right. This is the way the channels work. But it has two other interesting impacts. The first one's in music. As long ago as 1714, the Italian violinist Giuseppe Tartini noticed what he called third sounds, terzi suoni. They have since been called distortion products, difference tones, and so on, most commonly combination tones. He was tuning his violin, and he noticed when he played a high frequency F2, a lower frequency F1, he could, of course, hear those tones. He could hear the harmonics because he had a good violin, so he could hear the second and third harmonic. But he could hear things he knew shouldn't be there. He could hear F2 plus or minus F1, twice F2 plus or minus F1, twice F1 plus or minus F2. So he called these the devil's tones, which gave him, a sort of 1714 take on where they came from. It really wasn't clear what they were doing, but they're actually quite strong. In fact, they're strong enough that some subsequent composers in a number of different instruments have used them to create melodies. So Karlheinz Stockhausen, who also has scored things for machine guns and helicopters, did pieces in which two tone streams are played, but you hear a melody that's not being played because this nonlinearity causes this sound, 2F1 minus F2, to be heard by your ear, even though these two are really the frequencies being played. And the Hungarian-Romanian composer György Ligeti also made music of this sort. So I'll play you a short demonstration just to show you how strong these tones are. And the way the demonstration works is shown here. I'll play first a constant tone, F1, then another tone that starts out high and descends, F2. The strongest tone, as I've already mentioned, is twice F1 minus F2. So twice F1, which is not being played, would be up here. And twice F1 take away F2 starts out with a small difference, but becomes progressively larger. So 2F1 minus F2 starts out low and progressively rises. So the way the demonstration is contrived, you'll hear a constant tone and a falling tone. They're really there. But you can also hear a rising tone that I swear is not there. So here they are. Let me turn this down just a bit. Now the descending tone F2. Now the two together. Listen for the rising tone, particularly towards the end. So I can hear from the snickers that a lot of you can hear it. Let me play that again. Okay, a reasonable fraction hear it? And there are people here, there are students and postdocs from my group who can assure you that I would never lie to you. That was probably one of them. It really isn't there, and you can do this in more scientific circumstances with independent tone generators, independent amplifiers, and so on. So it turns out that this phenomenon, rattling around since 1714, stems from that nonlinearity that I showed you. That is from the fact that the hair cell steals a little bit of energy in each half cycle. Each time the hair bundle moves in one direction, a little bit of the energy goes into opening the channel. Each time it goes in the other direction, that energy is recovered as the channel closes. And that asymmetry produces this nonlinearity. The other consequence of the nonlinearity, which is rather neat, is its use in clinical medicine. I mentioned that it was a problem for years and years to diagnose young kids, particularly newborn kids, who had hearing problems. This provides a solution. So you take a device that simply plays into the ear from a simple microphone two stimulus tones. One tone, F2, that's higher than the other, F1. They go into the ear, and if the ear is more or less normal, the difference tone, 2F1 minus F2, will be produced, and some of that will be reflected back out. So then you just need a very simple meter that says, yes, that tone is there, or it's not. Now, some kids who flunk this test will have other issues. They may have water in their ear canals, for example, something really minor. So 2 days later, next week, they're fine. The great majority of apparent problems turn out to be illusory. But the important thing is that this means within a few days of birth, you can spot a kid who needs to be looked at in more detail. And then one can use other techniques such as auditory brainstem stimulation and the like, evoking electrical responses to see if hearing is really normal or not. And if it isn't normal, then one can first of all look into surgery, secondly look into a cochlear prosthesis or implant, which I'll describe later, or possibly go with American Sign Language. But one way or the other, the child will be dealt with within weeks of birth, or at least months of birth. In other words, the child will be given language at the time when he or she is passing through the critical period and most needs to pick language up. So it's really been a very valuable breakthrough. So far I've described the hair bundle as a recipient of sound, basically a transducer that captures physical vibrations, say from the sound in the air, and turns them into electrical signals. But it turns out that the hair bundle does a lot more than that. It's part and parcel of what's called the active process. So the active process is something that's found generically in amphibians and reptiles and birds and in mammals. In other words, all the tetrapods, the four-legged animals, have it. And it has four characteristics. Let's suppose we look at the basilar membrane, we shine our laser beam on it and look at it vibrating up and down at one particular position, and then ask how it vibrates as a function of frequency. So I'll look at the vibration as I play a high frequency, or as I play a low frequency, or other frequencies in between. And for any given position, I will find that there's a particular frequency that gives the biggest response. If now the animal dies, or more humanely, if one just compresses the blood vessels of the neck so that the ear is temporarily deprived of blood, the response falls to this blue curve. And this is a logarithmic scale, so it falls by 100 to 1,000 times. In other words, there's an amplifier normally present in each ear, like a biological hearing aid, that enhances the response 100 to 1,000 times. The second characteristic is frequency tuning. If we look at a normal ear, at one particular place, one particular frequency will give the best response. Again, if the animal loses its blood supply, that response falls. If we now turn the sound up 350 times, we will produce the same amplitude of response at the peak, but we'll get much broader tuning. And this is, in fact, the reason that hearing aids are so often unsatisfactory. Hearing aids make the sound louder, but they can't restore the normal biological sharpness of tuning, so one's ability to discriminate similar sounds deteriorates despite the hearing aid. The third characteristic, which is a little more obscure, is called compressive non-linearity. The idea here is that if you make the sound louder by 10-fold or by 100-fold, the response doesn't grow as much. In other words, there's sort of a compression. And this is the trick that allows us to accommodate this trillion-fold range of power into only about a 2-fold range in output. And finally, and most weirdly, is something called spontaneous otoacoustic emission. 70% of normal hearing people have sound that comes out of their ears if they're in a quiet enough environment. So if you go into a sound booth and we put a microphone in your ear and there's no sound at all, the odds are 70% that one or both of your ears will emit sound. A typical emission is what's shown here. There'll be 3 or 4 peaks, some big, some small. The world's indoor record is a woman who had perfectly normal, good hearing with 33 of these peaks. And some people have none at all. They're quite stable, so your left ear will be different from your right ear, but over years or even decades, they don't change much unless your ears are damaged, unless you are in a very loud environment, take one of the ototoxic drugs or the like. So what this is saying is not that it's useful to have sound coming out of your ears. The point of it is that the system has what's called gain control. If you're in a loud environment, you don't need this amplifier, so the system turns itself down. If you go into a quieter environment, it turns itself up progressively until you can hear a pin drop. And if you go into a super quiet environment, like a sound booth, it goes up to 11. And it then goes unstable and begins to vibrate, just as this public address system would if we turned it up too far. You would get feedback, hum, or howling. The ear does exactly that. So it's, again, an indication that the ear has an amplifier built into it and that system can go unstable. This is a demonstration of these otoacoustic emissions from a normal person. This is, of course, amplified a great deal. But in this case, there are two prominent emissions at these two frequencies. There are some other smaller ones. There's some background hissing. And you'll also hear heartbeat. You'll hear the stomach gurgling. You'll hear clothing move. Okay, so this is what you measure with, perfectly normal hearing. So it turns out that all four of these characteristics originate at the hair bundle. The hair bundle isn't just a passive receiver. It's, in fact, an active device that is producing each of these characteristics, and I'll show that briefly. First, amplification. If I apply the stick to the hair cell, as shown here, at first I measure nothing except vibration from molecules of water bouncing against it. But if I begin to move the base of this stick, the hair bundle begins to move in synchrony with the stimulus. So here the stimulus is, here the stimulus is being applied. We see oscillations of the base of the fiber. Now the hair bundle at the other end of the fiber begins to vibrate. You can see there's a nice one-to-one relation between the two, but the hair bundle is vibrating twice as much as the mechanical stimulus. In other words, there's amplification in the system. And the amplification can be much bigger than this, at least a factor of 10, or with multiple hair bundles, factors of 100 or 1,000. Next, there's tuning. So for a particular hair cell and a particular hair bundle, there'll be one particular frequency at which the response is the greatest and the sharpest. And if we move to higher frequencies or lower frequencies, we'll see a smaller response. If the hair bundle is dead, if it's passive, we get this very diminished response. Third, there's compressive non-linearity. So very weak stimuli evoke a very strong response. The response gets smaller and smaller. The sensitivity gets lower and lower as we go to higher and higher levels of stimulation. And again, a dead bundle just shows this passive behavior. And finally, the hair bundles can vibrate spontaneously. And that spontaneous vibration is what is necessary to produce the sound evoked from the ear, that is spontaneous otoacoustic emissions. So this lower hair bundle, which is seen from above here, is vibrating relatively fast and relatively smoothly. This one is more erratic and has a funny pattern of oscillation. If we put our stick on these and measure the oscillations, we find that different hair bundles have different sort of characters. Some of them are almost metronomic in their regularity. Some are fast, some are slow. Some are one-sided. Some are just ugly. Some of them show these large so-called relaxation oscillations with a fast component, slow component, fast component, slow component, and so on. And as I'll mention in a minute, we now understand what the differences between these turn out to be. If we look at a vibrating hair bundle, we see something extraordinary. I showed you before that the relation of displacement and force had sort of a kink in it. But in one of these vibrating cells, it's much more exaggerated. In fact, the curve shows this region with a negative slope, followed by this second region of linearity. Now, a region of negative slope like that is bizarre. It's something you mostly won't encounter, I hope, in daily life. And here's what it means. Hello? When the hair cell's at rest, the fiber attached to it is straight. If we move the base of the fiber well to the right, it pulls the hair bundle to the right, but the fiber being flexible, it bends back to the left, as you've seen before. The weirdness ensues if we move the base of the fiber just a little. Now we find that the tip of the fiber moves more than was asked. In other words, it's as though I walk up to something that is ordinarily rather solid, like the piano, and I push against it. Hello? And when I push against it, instead of pushing back, the piano instead pulls me farther in the same direction. It says the piano has in it the capacity to do work against me, against an external object. Similarly, this says that the hair bundle can do work against the fiber. So this is part of the amplification apparatus. It's also the case that between this point and this point that I've shown in pale blue, the system is unstable. If you place the hair bundle in the red region, it must jump over here or it must jump over there. It cannot stay in between, but always battering by water molecules will push it one way or the other. So anything that shoves the system into that red region will cause it to jump back and forth. And that's the basis of an amplifier or an oscillator. So in fact, what moves it into that region is a process called adaptation. I've shown you before that we move the hair bundle in the positive direction by applying a force to it. Channels open, and it turns out that calcium ions flow in, these sort of purple or puce things. They go inside and bind somewhere, and we still don't know where. But when they bind, the little gates close. And you can appreciate that when those gates close, they'll put more tension in the yellow gating springs, the yellow tip links. That extra tension pulls the system back to the left. So we've created a little machine. We apply a mechanical force to the right, and with the delay, it jerks back to the left. And you can harness such a machine to do work. Here's the way it operates. We're going to give a sinusoidal stimulus. In other words, the fiber will push the hair bundle back and forth and back and forth. Each time we push it first in the positive direction, channels open and calcium goes in. Now we begin to push in the negative direction, but when we're pushing in the negative direction, at the same time, the calcium that's entered closes the channels, and that produces the little red force back to the left. So in each cycle, calcium is doing some work. That red arrow is augmenting the work of the green one. It's an amplifier. And in fact, that has the right characteristics. If you drive it with a mechanical force, the passive hair bundle just produces a tiny movement. But the active hair bundle produces a movement that's 100 to 1,000 times as big. The system is highly tuned to a specific frequency. So for a given position, you'll find that it's most sensitive, it has the highest gain for the weakest stimuli. And as the stimulus gets stronger and stronger and stronger, the response, the gain gets weaker and weaker, so it shows a compressive nonlinearity. And finally, the system can go unstable. So if we give stimuli of constant size and turn the knob, turn the knob in the model, we'll get a small response, a progressively larger response, a progressively larger response. And finally, the thing will cross what's called a Hopf bifurcation, go unsteady, and begin to oscillate spontaneously. So this idea of a bifurcation is a common one in physics. The notion is that a bifurcation is a qualitative change in the behavior of something as you smoothly adjust a parameter. Let's say as you smoothly turn the knob. So to give you one example, this is a little piece of elastic. The piece of elastic is linearly elastic in one direction. So if I push it to your right, it moves a certain distance. If I push it twice as hard, it moves twice as far, 3 times as hard, 3 times as far. So that's Hooke's law. But if I move it in the opposite direction, it bifurcates. It undergoes an abrupt change. It's sort of sad, huh? An abrupt change in its behavior. So this is a particular kind of bifurcation. It's not a Hopf bifurcation, but it shows you at a particular point, the critical point, the thing undergoes this very abrupt change. The Hopf bifurcation is different in that it's oscillatory. The thing goes from being stable in the absence of a stimulus to unstable, and this is what we think causes the spontaneous oscillations, the spontaneous otoacoustic emissions. Now we can rather briefly characterize this behavior by looking at something called the state diagram. So this is a diagram for water. If we look at the temperature and the pressure, as you know, we can get gas, that is water vapor, we can get liquid, we can get various flavors of ice. Similarly with the hair bundle, we can control 2 dials, 2 parameters. This turns out to be the stiffness of our rod. This turns out to be the force we apply with the rod. And what we find is that there's a region in which the hair bundle oscillates spontaneously, as you've seen. This we think causes the otoacoustic emissions. And there's another region where it's perfectly stable, but it will respond to mechanical stimulation. Now, one of the things we're working on now, and the idea that I'm about to show you we think may not be right, is how this system adjusts itself in our own ears. Namely, if we're in a loud environment, it might be nice to operate over here, away from this region of oscillation and high sensitivity. If we move into an ordinary environment, things get more sensitive. If we're in a very quiet environment, the ideal position might be right there. And if we're in absolute silence, one would move farther into this fish-shaped object, and one would begin to emit sound from the ear. So we're trying to find out what is the knob that does this, or alternatively, what knob might make the fish bigger so that it encompasses a fixed operating point. In other words, you can imagine the blue point always prevails, but you get bigger and bigger fish until you begin to get the spontaneous oscillation. So that's the state of the art. I'll tell you now a bit about where things are going from here. This meeting is an extraordinary meeting, as Lars has already said. We're having a really stimulating environment because we're mixing together people with an interest in the more biophysical elements of hearing, such as myself, with those who are interested in the central nervous system and how sound processing and ultimately speech come out of all of this. This is a very rich environment for this, and in case you didn't know it, Lars probably doesn't know this, this is one of the preeminent areas in the world, preeminent institutions in the world where this is occurring. So along with Princeton and the Max Planck Institute in Dresden, KITP is one of the three premier sites in which physics and biology have been commingled in a productive way. So it's a very special place for us to be. So what kind of things are we looking for at a higher level? This is the brain. The cerebral cortex is known to you all, cerebellum, brainstem, and whatnot. We know a lot about the visual brain. The visual brain is here towards the back of the brain. It has a number of areas that are defined by their architecture and other criteria. And we know something about what they do. So here's a stimulus. This is stolen from the SpaceX website. It's also an acoustic stimulus, but so we see all this activity, and what does the visual brain do with it? Well, we know that the first area of the visual brain, called V1, looks basically at the outlines of things. It does a sort of Picasso-like rendering of edges. So the spaceship itself, the rocket, the towers around it, the buildings, the edges of clouds, and so on, get defined there. Another higher area, V4, adds color to the scene. So the sky color, the ground color, and whatnot. Another area called MT is interested specifically in movement of the system. So each of these different modalities is represented at a different place in one of these areas. And there are other areas like V2, which represents stereoscopic depth. There's this kinky area, IT, the infratemporal area, that responds just to faces. So we know this much in the visual system and much more. We know much less in the auditory system. The auditory cortex is here. There's a primary cortex and then a belt of various surrounding areas. But we don't know that much about how they operate. We certainly don't know the detail that I just showed you. We know that there are higher areas that are very poorly defined, like Wernicke's area, that are involved in the apperception of speech sounds. So people who have a problem in this area, like a stroke, will have what's called a receptive aphasia. They can hear, but they can't make sense of speech. We know other areas, such as Broca's area, that are involved in productive aphasia. A person there, with a lesion there, can hear okay and recognize speech, but cannot produce it. So we really need to learn what the wiring is among these areas, how information flows to this region, how ultimately messages get over to Broca's area, and then from there, down to the tongue, the larynx, and so on to produce speech. And there's some very productive work in these areas that we've learned about in the last few days at the presentations here. Another set of things we're doing is looking into how these remarkable structures, the hair bundles, are formed. They're remarkably regular, and they really look like they're stamped out by a mold or a cookie cutter of some sort. How can this be done? And it turns out that a physical model, due to Alan Turing, the great mathematician, can explain some of this. So this is the top of one of these cells, and you see the hexagonal pattern of the Stereocilia, the single canocilium. If you suppose that there's some pink chemical coming from the canocilium and some other green chemical coming from the boundary, you can make simple reactions and a prediction of how this would produce the pattern of a hair bundle. So you start out with this mess, nothing at all, but as soon as you turn on the reactions, something coalesces. And the something coalesces into neater and neater structures that look more and more like the hexagonal pattern of a hair bundle. So we're busy trying to understand now how this operates and also to demonstrate it experimentally. So with new microscopic techniques, it's possible to see hair bundles actually growing. So this is from a fish. This is a newly formed hair cell. This is a newly formed hair cell. As yet, they don't have hair bundles, unlike these more mature cells in which you can see the stereocilia sticking out. But in a time lapse over about 12 hours, watch these stereocilia grow. So here they come. They're getting taller, taller, taller. And we hope eventually to be able to follow them all the way to full maturity. So we're trying to test these ideas of the chemical reactions that produce these mature hair bundles. The final thing I want to deal with is the problem of what happens as these cells deteriorate. What can be done, in a word, about hearing loss? We start out with these beautifully regular hair bundles. With age, with chemicals, with sound damage, they become disheveled. And the bad news is that in mammals, when one of these cells is damaged, it always dies. It is not replaced by cell division. So it's like the cells of one's brain or one's heart. Once they're gone for good. And because each of these cells or groups of cells represents a particular frequency of sound, those particular frequencies are lost as well. So one place we've investigated this is the lateral line organ of the zebrafish larva. So zebrafish are little aquarium fish that many of you have raised as kids. Their larvae are just a few millimeters in length at age 1 week. And along their side, they have something called the lateral line, these yellow organs which have been stained with a dye, each of which is a cluster of hair cells. These hair cells reach out into the water and they feel water motion. So they can feel water moving past the fish, they can feel the fish moving through the water, they can detect predators, they can detect prey. They're a very important sense for these fish. Each of these little clusters, which is called a neuromast, has hair cells, red and green in this case, red and blue, sorry, in this case, and they're of opposite polarity. The two red hair cells have their tall edge to your right. They're sensitive to stimuli like the red arrow in that right direction. The two blue cells are symmetrical and sensitive to stimuli in the opposite direction. These are produced in an interesting way. The ear sits just behind the eye, but from the ear, a cluster of cells called a primordium streaks off down the length of the animal when it's 2 or 3 days old. And as it goes, this primordium deposits clusters of cells. So here's the primordium chugging along and a cluster of cells being dropped. And here's a quick time-lapse movie showing it. It's like a bus letting off passengers periodically and always dropping off about the same number. So the primordium is here. This is part of the tail of the fish. Here's one cluster of cells, a second cluster of cells, a third cluster of cells dropped off by this primordium. And finally, it gets down to the tail maybe a day or so later. Now, if we look at one of these clusters, we can see the hair cells developing within it. So to start, I want to point out this cell here, which is black at the outset, like these other black cells around. These cells that are fluorescent yellow or green are hair cells. There are in fact 1, 2, 3 pairs of hair cells here, 4 pairs of hair cells over here. This cell is turning green. It's decided it would like to be a hair cell, or more likely, it's going to be 2 hair cells. In just a minute, we'll see a very excited macrophage come. There it is. And this cell will now undergo a division. Pop into 2. Watch this cell. It's going to commit suicide. So it's gotten old and died. So there's sort of a conveyor belt system. New cells are formed at the North Pole and the South Pole. As they get older, they move to the center and eventually die and are replaced. Here's a schematic diagram of that. They're stem cells that are constantly making new cells, and they're always made in pairs. And interestingly, the pairs are always of the opposite orientation.
So one cell, the one on your right, is sensitive to motion to your left. The cell on your left is sensitive to motion on your right. These cells then in pairs move down towards the equator from both directions and then finally age and die. The reason I bring this up is that we can now use this system to try to decode the molecular and genetic pathways that are involved in this progression. What is the stem cell? What is this amplifying cell? And what are the series of reactions involved in the progression to new hair cells? By decoding that, we hope to be able to learn how to evoke something similar in the mammal, including the human. One other thing about this system that's turned out to be interesting and instructive is, as I've mentioned, the cells have two different orientations, some oriented towards the fish's front, some oriented towards its rear. Those different cells have different nerve fibers because they represent different things. One of them represents movement of water towards the fish's back, one towards the fish's front. So a single nerve fiber, such as the one marked in red here, comes in and it spreads over these cells and ends up at 4 days innervating just these three. You can see the little red spots, which are the synaptic contacts. And those three cells are all facing to your right. In other words, they're sensitive to motion to the right. This nerve fiber does not innervate the cells facing in the opposite direction. And in fact, there's another unmarked nerve fiber that does. So one wonders how the connection between these two is set up. And when we studied this, we found a great surprise. The supposition has always been that a hair cell just sits there waiting for a nerve fiber, here shown in magenta, to come along and make a contact with it. But what we found is that when newly formed hair cells are made, they participate actively in finding a nerve fiber. So when I play this time-lapse movie, you'll see this hair cell in particular put out a tentacle like an octopus, reach up and grab a nerve fiber. So here we go. Here comes the tentacle. It missed. Here comes the tentacle again. Now it's got the nerve fiber and it reels it in. This is something totally unanticipated. Nobody's ever made movies of this before. And it gives us new clues to look for the molecules that are involved in this interaction. The other system we and others are working on is the mammalian system, in particular mice. Now, in animals such as the zebrafish that I just showed you, if the hair cells die, there are left over so-called supporting cells that are normally between the hair cells. And in zebrafish, and indeed in reptiles and birds, these supporting cells will undergo mitosis. They'll split, making new supporting cells. And some of those supporting cells, say these two, will then turn into new hair cells and we'll be back where we started. This animal will be able to hear again. We can't do that. In mammals, what happens is that the supporting cells do not undergo proliferation. Instead, there can be some that turn into hair cells, but there are now too few supporting cells and the whole thing tends to die. And this is what we're left with, just the scar where the hair cells once were. So we're trying to find out how to deal with that using the utricle, which is another organ from the mouse's ear. Here's the cochlea. The utricle, which is easier to dissect, it's nice and flat, has on the order of 2,000 or 3,000 to 10,000 hair cells, shown here in this nice pink color. It's the organ, remember, that's sensitive to up and down and particularly side-to-side motions of the body, but the hair cells are very similar. And what we've done in this case is look at the capability of this utricle to make new supporting cells and new hair cells. So this white label, each of these white spots, represents a hair cell that's dividing. And what we find is at P0, which is the day of birth in a mouse, there are a lot of cells that are still capable of dividing. But just over a week later, there are only a few left. And this is a graph showing the same thing. Just after birth, the capacity to divide diminishes enormously. And for the rest of the animal's life, no new supporting cells, no new hair cells can be made. So we ask what genes are changing around that time. There are a number that were already known for various reasons, but we discovered this red group of genes called SOC changes abruptly. Their expression of each of these genes falls, except this one, which is a contrary gene, goes in the opposite direction. And this is very exciting because we can manipulate such genes. We can use a virus, for example, to re-inject these genes and turn them on. So here we have a utricle that's a couple of weeks old. There are no cell divisions at all in its interior anymore. But if we use a virus to inject this gene for SOX4 or the gene for SOX11, the particular molecule, as I mentioned, we turn things back on. So this is really a hopeful thing because it means we may be able to find ways of reinitiating the proliferation of cells and then the differentiation of new hair cells. Now, we don't want to do that with virus. None of us much wants viruses to be injected. But what one can do is to look for small molecules, that is drugs, that do the same thing. And our group has screened 65,000 small molecules and found a handful of them that have the right sort of effects. So we'll try these first in this preparation in a dish, and if any of those work out, then we'll try it in a real mouse and see what happens. So the last thing I want to mention is what happens until these strategies work. The answer is the cochlear prosthesis, the cochlear implant. And you already can understand how this works, because in the normal cochlea, as I've mentioned, a particular tone evokes motion of a particular group of hair cells. That activates a particular group of nerve fibers. If every hair cell has been effaced, one can nonetheless signal the brain that a particular note is being heard if one could use a little electrode like this red wire to shock just those nerve fibers. And you can imagine if you have an array of electrodes, you can shock different nerve fibers. The brain down at this end doesn't know the difference. It's still going to hear a middle C. And that's what the cochlear prosthesis does. Here's a diagram of the device. There's an external part that is worn these days just on an eyeglass frame or can be worn in a breast pocket. It picks up sound and breaks it down into a number of independent channels based on its frequency. And then it sends independent information about each frequency up a wire. That information is shot across the skin by magnetic radiation. So there are no penetrating wires that could cause an infection or the like, just magnetic waves going through. That's then picked up by an internal antenna, which goes down to the prosthesis itself, the implant, which is placed in the lower half of the cochlea. And if you look at any particular level there, you would see this plastic implant with paired electrodes. And the idea is, even though the hair cells are gone, electricity flowing between these two electrodes will excite the nerve fibers, which very conveniently survive in most patients, even though they've lost the hair cells. This is a quite old electrode. This is from a couple of decades ago. New ones are much cleaner looking and have more electrodes. This one is nice because you can clearly see it's plastic. It has a bunch of wires running inside it. And then it has pairs of platinum electrodes, each of which is going to stimulate hair cells in a particular position. Now what I'm going to do is to play you a very impoverished bit of human speech. This will be human speech in which only 5 frequencies are left. And I can tell you at the outset that you will not understand it, but it will give you a sense of what the earliest prostheses were like. So I hope nobody could understand a word of that. But now 10 channels. And 10 channels is what the first fairly successful devices had. And you may pick up a word or two. So what did you get? You got something. Nothing? 1,000? Okay. So the next one is 20 channels. And 20 channels is about what a contemporary device has. I mean, there are various flavors. There are 3 or 4 major companies. But you'll definitely get a few words from this.
The Doppler Prosthesis is now in everyday use by nearly 100,000 people worldwide.
So what did you get? 100,000 people. Prosthesis. Right. So here's the original thing. The cochlear prosthesis is now in everyday use by nearly 100,000 people worldwide. So it's now 300,000 people worldwide. But get this, I'm going to play the 20 channels again, the one you didn't much understand. Your brains have changed.
The Doppler Prosthesis is now in everyday use by nearly 100,000 people worldwide.
And this happens with patients. People who've been deaf, for decades, get up off the operating table and they hear a couple of seconds of speech and they can understand it. So despite the great distortion, this is by far the most successful neuroprosthesis. And of course, it sort of paves the way
for efforts to develop a visual prosthesis for the blind, to develop spinal prostheses for people with various types of paralysis and so on. And it will be, for some of us in this room, a solution to hearing loss until we can find a way of regenerating the hair cells. So I'll stop at this point, and I'd like to thank you all for your patience.
Well, I'm sure Jim would love to hear some questions.
Do we have to pat? Okay.
To the microphone.
Do people generally lose the high frequency? Do they generally lose the high frequency first?
Yes.
And why is that? And what can be done about that?
Well, I can answer two of them. The answer is yes. High frequencies typically go first. We don't really know why, but consider the fact that the high frequency hair cells, when stimulated, are vibrating 20,000 times a second. So they're taking a real mechanical beating. At the other end, the apex, those guys are vibrating 20 times a second, so 1,000 times less. So some of it is simply the stress of very strong stimulation. The other thing is the stimulus comes in at the base. That's the high frequency end. So every stimulus, including the ones for the low frequency cells, first stimulates these to some extent, and later the signal gets up to this point. So these are stimulated only by the relevant frequencies. These are stimulated by everything. So they simply take more of a beating. Unfortunately, we can't do anything about it. So I have lost my frequencies from 20,000 down to about 12,000 from various abuses having to do with music and drugs, and not legitimate drugs in this case. So far, this doesn't much affect my speech perception. But what happens as the ceiling comes down and one begins to lose 10 kilohertz and so on, it begins to cut off the consonants at high frequencies, particularly women's voices, particularly your wife's voice. So this is a common complaint, that your husband is no longer listening and so on. And he may or may not be, but he will be tending to hear your voice less well than you can hear his.
Okay, two points. I guess one, I started losing my high frequency hearing, as most of us do, in the room when the speaker gets up with a microphone. As soon as the low frequencies come out, it blocks out the highs and it's hard to understand. Now, I got my hearing aids on today, so I can understand you. Thank you very much. Sure. But talk to them about that. Maybe you can tune it a little better for some of the people. And the second, the tinnitus, the ringing, ear ringing, is there any work done on that?
Right. There's a lot of work being done on it, and this is a very common complaint. So tinnitus, and I emphasize tinnitus, US at the end, is the preferred pronunciation. Itis, I-T-I-S, is the common ending in medicine for an inflammation. This is not an inflammation. So tinnitus means a ringing or bell-like sort of sound in the ear. There are a variety of causes. So there's some drugs that cause it, quite benign drugs. Strong doses of aspirin. So people used to take 4 or 5 grams a day before the NSAIDs and things like that came along. Or quinine for malaria. Those drugs cause ringing in the ears because they excite the nerve fibers. There can be ringing in the ears owing to this active process. I told you that sounds can come out of the ears. Occasional people have what's called objective tinnitus. That is, they have sound coming out of their ears even under normal circumstances. So somehow the thing is turned up to 11 and it's stuck at 11. It doesn't turn itself back down. But that's quite rare. Most tinnitus is like phantom limb pain. So as you know, if you have an amputated limb, often you will continue to feel the hand, maybe feel different postures of the hand, maybe feel burning sensations and so on. And the reason this is thought to occur is that the impulses normally running from nerves in the hand to this part of the brain on the other side have been interrupted. The brain is looking for inputs and it becomes more sensitive. It basically turns itself up until it begins to get spontaneously fictive or really fictitious inputs. Those are experienced as phantom limb pain. Similarly, if you've burned out hair cells, particularly at the high frequencies, that portion of the auditory cortex doesn't have input. It now tends to produce spontaneous sounds, which we interpret as tinnitus.
For those who have it, there is no wonderful cure for it. The best thing one can do is to mask it. So any sort of white noise, if you happen to have an ocean, that's good. But anything, whooshing noises, shh type of white noise, tends to turn the auditory system down and to suppress that effect.
Can you talk about the relationship between vertigo, various forms of vertigo, and as I had Meniere's, and that I had understood that it was the tinnitus, say that right, that caused my hearing loss, but it's sounding like you're saying that that probably is not correct. Can you talk about that?
No, that isn't quite the case. So the condition you've mentioned, Meniere's disease, is something that we don't understand well in terms of its origin. And different people have different degrees of it. Let me go back to this picture of the cochlea and the rest of the labyrinth. In Meniere's disease, there is a swelling of all of these pipes and tubes. So all of the stuff, including the cochlea, is connected, even though it doesn't look obviously here. But these are little tubes. They're filled with a particular type of liquid. And in Meniere's, that liquid somehow accumulates excessively. When that occurs, there are a variety of symptoms. In the cochlea, it causes tinnitus. In these other organs, it can cause vertigo, so a sense of spinning around or whatever. Or if it excites these organs, the utricle and the saccule, as I mentioned, those are involved in your perception of which way is up or down. So there are people who have Meniere's who will be walking along and then suddenly fall to the ground. Because, I don't know if you've experienced that, but it can be extremely abrupt. And some people have to be cautious, for example, when driving a car or the like, because it can come on very suddenly and cause a catastrophic, imbalance in an automotive accident. So unfortunately, there are drugs that help with it, but we have no cure for that one as yet.
Animals like bats and whales, dolphins, etc., and even wild dogs have vastly different capabilities. Are there things we are currently trying to learn from them that might help with the prosthesis?
I'm not sure if they'll help with the prosthesis directly, but we're certainly learning a lot of things from this. We've had several nice presentations this week about bats and so on. The striking thing with bats, as most of you know, is most of their frequencies are so high we can't begin to hear them. Bats go up to about 200 kilohertz, so 10 times as high as we do. And they do something rather marvelous. Two cool things. First of all, a bat says, and I quote as it's chasing an insect, downshifted, "Eep, eep, 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 eep." So what is happening? Two kinds of sounds. You want me to do that again? The first tone, the "eep," is a constant tone. Now the constant tone goes out, it hits the insect, and it bounces back. But there's a thing called Doppler Shift, right? If you hear a siren go by, it goes to a lower frequency as it passes you, a higher frequency as it's approaching, and so on. Same thing with a bat and a bug. If the bat is approaching the bug, then the sound that comes back will be at a higher pitch than the sound that it emitted. So the bat not only can tell there's an insect there, but it can tell the relative velocity of the two. Is it gaining, is it losing, or whatever, and how quickly. Then the second part, yoop, so eep, the yoop part is a spray of different frequencies of sound. That is like color vision, right? You're sitting here in this room, you're bathed in white light. So I see different colors because the white light hits your jacket and I get green back. It hits your shirt and I get blue back. Yours, I get rose. We get so all these different colors. In the case of the bat, it's bathing things with different sound frequencies. And the bats can distinguish, for example, textures. So it can tell my shirt texture from your shirt texture, from the smooth piano, from the rough rug, and so on. It can therefore feel what the insects are like. The other thing that insects are doing, of course, is fluttering. So the bat also hears woof, 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 coming back as the insect beats. So the bat can decide if it's something it likes that day, if it feels like a snack, if it would rather pass because that's a poisonous insect. It gets all that information from this mechanism.
In the case of a person who has reasonably good hearing in both ears, if there's a sudden degradation in one ear, say maybe 25 to 30 dB within a year, does that imply that it's not in the cochlea, it's probably in the mechanical system? No.
It doesn't imply anything. I mean, it could be either thing. So one just needs to get proper audiology. And if people have a problem, there's a very simple test that's done called the Renee Test, and the idea is the following. You just take a tuning fork. I don't happen to have one, but you hit a tuning fork and you hear how loud it is. And then you take the same tuning fork and press it against the mastoid process, the back of this bone. If the ear is plugged, if the ear has problems with the malleus, incus stapes, and so on, when you do that, the vibration goes through the bone, and if the cochlea is normal, you'll hear it much louder. You hear this weakly, now you hear it louder. If it does not occur, though, there's going to be more likely a problem in the cochlea itself.
Okay, I would like to go ahead and thank Jim for his talk. And as always, we do have refreshments near the courtyard, so feel free to stay, and I'm sure Jim will take more questions, but he might want to drink first.
Definitely.